Okay, so in this video I want to introduce some of the basic ideas behind natural deduction and talk about the simplest natural deduction inference rules, and then illustrate how you can use those rules to build a proof in natural deduction. So with natural deduction, the idea is that you are given a set of inference rules which have names. In this chapter, or this unit, we covered just a few of these, such as conjunction, simplification, addition, modus ponens, and modus tollens. So that's all we'll cover for this section. But there's a list of these rules, and the way you can think of it as kind of like a game or a puzzle where you are starting with the premises. That's your starting point, and you have to, the conclusion is kind of the goal of where you're headed to, and you have to figure out whether there is a path from the premises to the conclusion using only the moves defined by the inference rules. Okay, so is there a way to get from the premises to the conclusion using only these rules, applying them step by step? Okay, so let's talk about some of the basic rules, and then we'll see how you can go about applying them. So one of the simplest inference rules that you will encounter is known as conjunction. So with conjunction, what conjunction tells us is that when we have a line in our proof such as P, and we have another line in our proof such as Q, then you can form a new line of the proof, which is the conjunction of those two statements, namely in this case P and Q. So why is this a legal move? Well, again, a conjunction requires each individual conjunct to be true. So if we have a proof and one of the lines tells me that P is true and another line tells me that Q is true, then I know that P and Q are both individually true, so I know for sure that I can combine them into a conjunction, as we see here. Now, this is just, we're using P and Q as examples here, but these can stand in for propositions of any complexity, right? So for instance, if I had something like this, P or R on one line, and then I have Q on another line, then I can apply conjunction, just like this, to form the conjunction of this line and this line. Okay, so in all of these cases, we'll illustrate these by using simple variables such as P and Q or R, etc. But you should understand that these rules apply to statements whether they are atomic propositions or complex propositions. Okay, so this is also a valid application of the rule of conjunction. Whenever you have a proof where you have one line asserting something and another line asserting something else, you can always combine them with the conjunction. And when you do that, you form a new line in your proof, and you would cite the rule that you used to get to that line as conjunction, and then you would cite the lines that you used, that you are conjoining. Okay, so let's move on and see how some of these other rules work. Okay, so simplification is again a rule related to conjunctions, so it's kind of similar to the previous rule, but maybe going in the other direction. So with simplification, we start with a conjunction, such as P and Q, and simplification tells us that when we have a conjunction, you can always infer each of the individual conjuncts on their own separate line. Okay, so if I have a proof which has a conjunction, say P and Q at some point, then I can immediately infer P. Or because the order of the conjuncts in a conjunction doesn't really matter, similarly, if I have P and Q, I could also use simplification to infer the second conjunct as well, directly. Okay, so it can work either way. And again, just to be totally clear, this does not simply apply to atomic variables. So if I have a proposition like this, P implies R and Q or S, let me move this out of the way. So if I have something like this, P implies R and Q or S, here I have a conjunction with this on one side and this on the other side. So those are my two conjuncts. So simplification tells me that if I have this in my proof, then I can form a new line in the proof which has just the left conjunct. Okay, that would be a legal move. That would be a valid move. Or if I wanted to, I could apply simplification and draw out the second conjunct instead. Okay, so simplification is a rule which takes you from a conjunction and allows you to infer each of the individual conjuncts. So it's kind of like the opposite of conjunction, right? Just to simplify this again. With conjunction, you have a proof where you have each of the individual conjuncts stated independently on different lines, and then you combine them into a conjunction on another line. With simplification, you start with a conjunction and you infer one of the individual conjuncts on a new line. Okay, so very related rules, but hopefully quite intuitive as to why this is a valid move in the game. Okay, so now let's look at addition. Addition is a rule that's to do with disjunction rather than conjunction. So with addition, you can see that what it tells us is that if we have a proof which has any given line, say P, on one line, any given proposition on one line, then you can immediately infer a disjunction with that proposition on one side and some other proposition, any proposition at all, on the other side. Okay, so Q is kind of coming out of nowhere in this case, right? We're starting with P, and then we're just inferring P or Q. On the right side, I'm just illustrating that you can do the same thing with any variable whatsoever. Or even if I wanted to do something like P or Q and S, that would be perfectly legal as well. Okay, so why is that? Why is this a legal move? Well, think about what disjunction means. If a disjunction is true, it requires that at least one of the disjuncts has to be true. Okay, so if P or Q is true, then either P has to be true or Q has to be true. Right? So now if we look up at the top, we have P. We have asserted one of the disjuncts. So we already know that one of the disjuncts is true based on this line. So we could immediately infer that any disjunction that you add, any proposition that you add to that proposition using disjunction will create a true disjunction. Right? So if you start with a true proposition, you can add any statement whatsoever to it with disjunction, and you will also get a true proposition. Of course, that's not the case with conjunction. Right? I can't go from P to P and Q. That would be wrong because P and Q would require both P and Q to be true. Whereas with P or Q, we only need one of them to be true, and we have up here already been told that one of them is true. Okay? So with addition, you can start with a proposition, and then on a new line, add any proposition you like to that proposition with a disjunction. Okay, so now let's look at two really important rules that definitely come up a lot in logical thinking. One is called MODUS PONENS, the other is called MODUS TOLENS. So both of these have to do with the use of conditional statements. So with MODUS PONENS, we are told that if we have P implies Q on one line, and then P independently asserted on another line, then we can infer Q as a result of those two statements on a third line. Okay, so what does this mean? Well, again, P implies Q tells me if P is the case, then Q is the case. And then here we're told, okay, P is the case. So if P is the case, then Q is the case. In fact, P is the case, therefore we can be sure that Q is the case. So this is kind of the basic idea behind a conditional statement. Right? You have this conditional, and then if you are able to assert the antecedent independently, then you can assert the consequent independently. Okay? Now, MODUS TOLENS is kind of the opposite of MODUS PONENS, in the sense that we start with P implies Q, or if P then Q, but then on the second line, we get not Q. Okay? And if not Q is the case, then we can infer that not P is the case. So MODUS TOLENS kind of reverses the direction of MODUS PONENS, because whereas with MODUS PONENS we have a conditional, we assert the antecedent, and then we get to assert the consequent. With MODUS TOLENS we have a conditional, and then we get to deny the consequent, or rather assert the negation of the consequent, which is this, then we're allowed to assert the negation of the antecedent as well. So for an example of that, if you have a statement such as, if John is home, then the lights are on. That would be if P, then Q. If John is home, then the lights are on. The lights are not on, so therefore John is not home, right? That's basic reasoning. If P, then Q, actually not Q, therefore not P. Okay, so hopefully you get some intuitive sense of why this is a valid rule as well. Okay, so now let's see if we can apply these basic rules to build some proofs for some basic propositions and apply, this procedure and illustrate how you go about actually building a proof. Okay, so here we have a really straightforward proof with a rather complex premise. In this case, it's P and Q and R and S and T. Okay, so many conjunct together. And the conclusion we want to reach is simply S. Okay, so we have to figure out, is there a way to get from this statement to this statement using only the rules that we've covered so far? In fact, in this case, I'm going to show how to do it simply using the rule of simplification. Okay, so with any proof, the first thing you have to do is write the premises down. So let me copy that down. Okay, P and Q and R and S and T. Okay, then for each line you also have to indicate the justification for that line. So if it's a premise, you can simply write that it's a premise. Okay, so now we have to try to find S. Now we see that S is located all the way in here. It's kind of way buried deep inside this complex proposition. So we have to figure out how to break down this proposition in order to isolate this one part of it right here. So first thing you have to be able to do is identify the main operator for this proposition. So what is it in this case? Well, we have a lot of conjunctions, so the main operator is definitely going to be a conjunction, but which conjunction is it? Well, here we have one conjunction which is surrounded by parentheses. And here we have another set of conjunctions which are also surrounded by parentheses. So this is actually going to be the main operator in this sentence, with these two sides as its parts. So we could apply simplification to this complex proposition. Okay, so one thing we could do is apply simplification to the left side and infer P and Q. Right? That would be using simplification to draw out the left side of the conjunction. But if we think about it, we're trying to reach the proposition S. So if we apply simplification to the left side, it doesn't really seem to be getting us much closer to our goal. Right? So what we really want is to deal with the right side. So rather than doing that, let's apply simplification and infer the right side of the conjunction, which is that complex proposition itself. Okay, so now I have to indicate how I arrived at that line. All right. And I have to provide the line number that I used to get there. So in this case, it's 1. So I applied simplification to line 1 in order to get line 2. Okay, so now what do I do? Now I have a simpler statement, and I'm still not quite at my goal, which is S, but I've broken things down a bit, and it seems like I'm getting closer. So what I can do is simply apply simplification again. Now I have a choice here, right? There's two sides to this conjunction, so I could apply simplification and get R. Okay, but again, that doesn't really help me get to my goal, which is S. So when you're building these proofs, it's never necessarily a bad thing to write unnecessary lines. Like if I were to write R here and say simplification, line 2, that wouldn't be wrong, and I could continue on with the proof, but it wouldn't really help me. So you can't really be graded down for putting unnecessary lines in the proof, but just for your own sanity, it's probably best to just stick to whatever is helping you advance your goal. So we know that really the right side of the conjunction is what is going to be useful for us. So let's apply simplification again. And this time, again, we'll infer the right side of the conjunction. So let's make a note of that. Simplification. And here we have used simplification on line 2. Okay? All right, so now we're a little bit closer to our goal. Now, how do we get from S and T to T? Now we're simply applying simplification to a conjunction with two atomic propositions. So this is exactly like the rule as it was described on a previous slide. So we have S and T. We can directly infer S, again by using simplification. This time on line 3. Okay, and so S was the conclusion. That's what we were trying to prove. So we have figured out how to show a path leading from the premise to the conclusion by applying just the rules that we've learned so far. In this case, only one rule, that is simplification. Okay, and what's important to note here, at least one thing that you should notice, is even though we're applying simplification over and over again, it's important to actually go through it one step at a time. Right? So it would be wrong if I were to simply cut these out and go directly from the premise to the conclusion using simplification. Right? You can't do that. You can't just skip lines. You always have to go one step at a time. And this way, basically, the reasoning that you've used to get from the premise to the conclusion will be very clear and obvious to anyone who wants to evaluate, the proof and see whether it really is valid. Okay, so let's look at another example, one that doesn't just simply use simplification. Let's see. Okay, so here we're dealing with, again, we have to write down premise first. So let's just copy that. And we indicate that it's a premise, so it doesn't really need justification. Okay, so what are we trying to do here? We're trying to get to P and Q. Now, how are we going to do this? Seems like P is over here, so that's going to be probably something that we're interested in. So we could apply simplification to pull out the, wait, this should be P or Q. Pardon me. I think that should be a little bit easier. Okay, so let's see if we can use this to get to P or Q. So again, we'll start similarly to the way we started the last proof. Okay, by applying simplification. And again, this is a complex proposition, but the main operator is again conjunction, with this being the left side conjunct and this being the right side conjunct. Okay? I'm sorry, I think this was supposed to be P and R. Either way. Okay, let's go with that. There we go. Okay, so here, let's, sorry about that. So let's try and prove P and R. So first we need to draw out the left conjunct using simplification. This is just like the previous proof. Okay, now what do we do? So let's see. So we're trying to get P and R. Can we use simplification to get P and R? Well, let's see. We could use simplification to get P at least. That's getting us closer, perhaps. So let's do that. Simplification on line 2 to pull out the P, the left side. Okay, now how do we get R? So if we were to apply simplification again to this, then we would get something like Q or R. But how is that going to help us? Because what we really want is to get P and R. And if we get Q or R, well, we can't use simplification again because this is a disjunction. You can't apply simplification to a disjunction. All right, so I can't infer R from Q or R. So that doesn't look like it's actually going to help me. So, okay, let's go back to the drawing board and take a look at the original proposition and see if we can work with the right side at all. Okay, so with the right side, let's apply simplification once again. And this time we're going back to statement 1, and we're applying simplification to infer the right side conjunct. Okay? So simplification on 1 again this time. Okay, now again we're trying to get P and R, so let's see, how can we do this? They don't appear anywhere actually in this statement, so what can we do? Well, if I actually were able to infer P on its own, and I was able to infer R on its own, then I could actually combine them using that rule of conjunction. So maybe that could be a strategy I could pursue. So here we have R and S if and only if T. Again, this is a conjunction. So since it's a conjunction, I can apply simplification once again. So we don't really care about this part because that's not relevant to our conclusion. So we'll focus on the left side and we'll use simplification to get R. Simplification on 4. Okay, so now what do we have? Seems like we've got all the pieces that we need. We're trying to get to P and R. Here we've got P. Here we've got R. So we know for sure that P is true, and we know for sure that R is true. Therefore, their conjunction ought to be true as well. So I can just apply the rule of conjunction to combine, lines 3 and 5 to get P and R. Right? So if we go back to our rule of conjunction, this tells me that if I have P on one line and Q on another line, then I can combine them to P and Q. Here I've got P on one line and R on another line, so I can combine them to form P and R. And that is our conclusion after I've made some edits. But I think this proof works out very nicely to illustrate at least the combination of two rules. Okay, so these are very basic, just to give you an idea of how this kind of flow works, and the fact that you can apply these rules again and again, and how to combine these very basic rules. So it's really good to get comfortable with these kinds of simple proofs, because as we add more and more rules to the game, it'll be easier to find what moves to make in what circumstances. Okay, so let's look at a couple more examples just to get some more practice. So here we have a little bit more complex statement. So 3 premises here. P and Q implies R, P and S, and third premise Q. And what I want to infer is R or T. Okay, so how do I go about this? So I just want to walk through this again just to kind of give you a sense of how you might approach this kind of proof, so that when you do it on your own, you have some guidance. Okay, so again, the first thing to do is easy. Always start by listing the premises. So P and Q implies R. That's a premise. P and S. That's a premise. And Q is also a premise. Okay. So now we're trying to get to R or T. So one thing I notice is that R is over here on the right side of this conditional. So I need to be able to access this somehow. So I'm thinking that I should apply one of the rules for conditional at some point, perhaps modus ponens. So if I were able to get P and Q on its own line, then I could use modus ponens to infer R based on P and Q, and then maybe that would help me go from there. So again, this is one way of thinking about it, like find the goal and then look at other things that you might need to help you get to the goal, and then come up with strategies to reach those intermediate points, kind of breaking the problem down. And this might help you rather than getting overwhelmed by seeing all these propositions at once. Okay, so let's see if I can practice that. So see if I can try and make P and Q. Well, what do I have to work with? I have P and S here, so why don't I just try and apply simplification, see if that helps. Simplification is kind of a good rule to start with because it always helps break down complex propositions into less complex propositions. It's a pretty easy rule to apply. Sometimes you might apply it and it doesn't help, but it can't ever really harm you to get to give it a try. So let's just see if it helps to apply simplification to line 2 to infer P. Okay. Now let's suppose I'm really stuck, so I go ahead and I apply simplification again just to infer. This isn't really going to help me, but I just want to show you that, okay, if you're stuck, maybe just start trying things and maybe they'll pay off, maybe not. If it doesn't, no big deal. I've added a few lines to my proof. I have P and I have S here. So I'm trying to get to R, or at least R or T. We'll worry about the T later. But I have P here on one line and Q here on another line. So remembering the rule of conjunction, one thing I could do is actually combine them just like this. So conjunction of lines 3 and 4. Okay? So 3 gives me Q on its own, 4 gives me P on its own, so I can combine them using conjunction to form P and Q. Okay, now, does this help me? Well, okay, now let's see. So here, again, we're dealing with a conditional, and the antecedent is P and Q. So if you have a conditional, and you can independently assert the antecedent, then you can assert the consequent as well. That's what modus ponens tells us. So here I have this conditional, and here I've actually asserted the antecedent of the conditional. So I can use that to apply modus ponens to infer R from lines 1 and 6. Okay, so just to go over that again, modus ponens says that if you have a conditional, then when you have the antecedent as well, you can infer on a new line the consequent. So this is a conditional with a complex antecedent, which is this conjunction. Here I have used some rules to infer P and Q, which is the antecedent, so I can use modus ponens to get to the consequent. Okay, now I've got R, and it seems like I'm almost at my goal, but it's R or T. So what do I do? Well, if you recall the rule of addition, addition tells me that if I have any proposition asserted in my proof, then I can add any proposition whatsoever to that using disjunction. Right? So I can create a disjunction from a known proposition and combine it with any proposition whatsoever. So here I have R, and if I have R, then I can also infer R or T using addition. Okay, so this is a little bit more complex proof, a couple more steps. You see here, this step actually didn't help at all because I didn't end up using S, but okay, no big deal. It wasn't a huge waste of time. So I applied simplification, conjunction, modus ponens, and addition, and by chaining these together one by one, I was able to figure out how to get from the premises to the conclusion. Right? Now, one thing you'll notice when you practice these yourself is this is in some ways more interesting and hopefully more fun and challenging than doing a truth table proof, but it's also a little bit more difficult because it's with truth tables it's kind of a mechanical procedure. You just go from one line to the next and apply the rules that you have to for that column over and over again, etc. But here it's not obvious. No one tells you which rule you have to apply at a given step, so you have to kind of use your creative thinking to construct the proof. Okay, so a little bit more creativity involved in these. Okay, I just want to go over a few more examples just to help you really solidify what we've been talking about. So let's take a look at this proof. Okay, here I have a conditional statement with a complex consequent, and here I have the negation of that consequent. Right, so that's one thing I notice about the structure of this proof. I have P implies Q and R, and here I have not Q and R. So this is actually the negation of this. That's going to be interesting. Okay, so the conclusion is not P and not Q and R. Okay, so what's going on here? Well, let's just start however we know to start, again, which is always by putting the premises down. All right. Okay, so I've listed my premises. Now, what am I going to do here? So it might be that you're kind of stuck. In this case, I think there's pretty much only one rule that you can apply. So let's think about the rules that we have. There's no conjunction here, no disjunction, so it's probably not going to be one of those. So we've talked about two rules which have to do with conditionals, one being modus ponens and one being modus tollens. So with modus ponens, we have a conditional and we're looking for the antecedent of the conditional. But we don't have the antecedent here. There's no P here. So with modus tollens, actually what we're looking for is the negation of the consequent. And you can see that's exactly what line 2 is. So what we can do is apply modus tollens from lines 1 and 2 to infer the negation of P. So just to refresh your memory, with modus tollens, if you have a conditional and the negation of the consequent, then you get to infer the negation of the antecedent. So similarly, we have a conditional, the negation of the consequent, so we infer the negation of the antecedent. All right. Okay, so we've got not P, and we're just trying to figure out how to get not P and not Q and R. So what rule do we need to apply here? Well, let's see. Actually, if we look up at our proof, we have here on line 2 the other side of the conjunction that we're trying to make. Right? So again, if you think about the rule of conjunction, we have one line which says not Q and R here, another line which says not P here, so we could combine those. We know that these are both individually true, so we can combine them into a conjunction as well. Conjunction on lines 2 and 3. Okay, so this was a little bit more of a direct proof, but it gave you an illustration of using modus tollens, and also the fact that, again, these rules can be applied to either atomic propositions or complex propositions. What really matters is the shape, that they fit the pattern as defined by the rule. Okay, so just one more, just for practice. If you want, you can take a look at this proof and maybe pause the video, see if you can figure out a solution for it. And then we'll come back and go over it together. Okay, so how am I going to go about this? So this is a little bit more complex. 3 premises, not entirely obvious how I'm going to get to this conclusion. So let's see, what do I do? Okay, well, let's just start easy. Let me start by listing the premises. Okay, so P implies Q, P and R, and S implies not Q or R. All right, so now what do I do? Let's see. Not S and P. How am I going to get to not S and P? Well, I'm looking for P. That's part of it. So, okay, I have a conjunction here, which P is part of. So I could actually apply simplification and directly get P. Maybe that would be helpful. So let me just do that. And as you can see, this gives you some sense of how I might think through this if I were to approach this proof, for the first time. So simplification is always a good way to start. So I've got P now. Do I want to also apply simplification to get R? I could use that to get R here, but I'm not sure that that's going to be so helpful. Although actually we could do it that way. Well, let's just see. Let's try another strategy. I have P, and let's see. I have here a conditional. P implies Q, so I could use modus ponens. Right, I have a conditional, and here I have the antecedent, so I could also use modus ponens to get the consequent. Modus ponens from 1 and 4 would give me Q. Okay, now I have Q, but how am I going to do this? Well, okay, let me start thinking about what I need here. I need not S. And here I have a conditional with S as the antecedent. So maybe one thing that would be nice if I could apply modus tollens, then I could derive the negation of the antecedent of this, which would be not S. So again, that's thinking about, like, it's not obvious to me how I'm going to do that, but if only I could apply modus tollens, then that would help me get to my goal. So now I'm going to try and think about if there's a way if I could apply modus tollens. So if I want to do that, I would need to derive the negation of this part. So the negation of not Q or R, which would be Q or R. Okay, so let's see. So if I could get Q or R, then I could apply modus tollens to get not S. So let's see. I have Q here. So one thing I could do is I can simply add R using the rule of addition. Right? Addition tells me that if I have a proposition on one line, I can create a new line and add any proposition to that using disjunction. So I've got Q here, and I use addition to get Q or R. Now, Q or R is actually the negation of not Q or R. So since I have the negation of the consequent here, I can use modus tollens to infer the negation of the antecedent. Okay, if that move wasn't clear to you, then review the the rules for modus tollens, because it tells you that when you have the negation of the consequent, you can infer the negation of the antecedent. And here we did derive the negation of the consequent. So we get to derive the negation of the antecedent, which is S, and the rule is modus tollens from 3 and 6. Okay, now we're really close. We're trying to get not S and P. Oops. We've got not S, and we've got P, so all we have to do is combine them using conjunction. Conjunction on lines 4 and 7. Pardon me. Yep, that's right. Okay, so this was a nice proof because it actually utilized all 5 of the rules that we talked about for this section. And yeah, so hopefully you were able to follow along this proof. There was actually a different way that I noticed that we could have gotten to where we're going. If you look back here, on this step we use simplification. Maybe I'll just illustrate this alternative proof very quickly. Here we used simplification to get P from P and R. We could have also used simplification again to get to R. right? Using simplification to get the right-hand disjunct. And then this time we would have used addition from line 5 again, but this time adding Q to the R. So with that simple change, we would have a different proof, for this same argument. So what this illustrates again is that there's not only one path in every given case from the premises to the conclusion. So again, some creative thinking might be required. Okay, so hopefully that gave you some practice with the basic proof rules. And in the future, we'll be learning more of these rules and understanding more complex proofs. But it's just going to be, using these same kind of strategies, and practice is going to help you a lot as we go along.